Give a brief introduction about Professor Lanza. Professor Lanza got a PhD in electronic engineering in 2010, and after that he was a postdoc at Peking University. And in 2012 and 2013, he has more career postdoc at Stanford University. And then he joined Suzhou University as an associate professor. And he was also my PhD supervisor in Suzhou University. So today I'm very happy that he gave this plenary talk. And now Professor Lanza is an associate professor at the King Abdullah University of Science and Technology. And he has published over 120 research papers, including 2 science and 5 nature electronics and 10 advanced materials, and has registered 4 patents. And he's also the committee members of some the IEEE EDS, and also the editor-in-chief of the Journal of Electronic Engineering. So Professor Lanza's group, they investigate how to improve electronic devices and circuits using 2-dimensional materials with special emphasis in memory-resistive device and circuits. And today the title of his talk is the importance of miniaturization, electronic phenomena at the nanoscale. Okay, let's welcome Professor Mario Lanza. Hi, Mario, you can share your screen.
Yeah, thank you very much for your nice introduction and for the invitation and for congratulations for the organization of this nice workshop. So yeah, I have been studying materials and devices with conductive atomic force microscopy for the last 12 years, I would say even more, probably 16 years. And today I have updated some of the slides that I normally present because I wanted to emphasize one behavior that, especially recently, we have observed to be especially important. Because we have recently noticed and realized in a much more deeper way the very big differences that appear when you measure one electronic device that is big and the same electronic device that is small. Well, actually, the word the same doesn't apply anymore, as you will see. I think understanding the difference on these devices is essential to understand the importance of scanning-proof microscopy. So I have prepared a talk that has 4 sections. The first one is the introduction to resistive switching, which is the type of physical phenomenon that I'm going to talk about. I will first talk about the applications, and then I will go a little bit deeper into why miniaturization of resistive switching devices is important. And finally, I will show you how we study resistive switching with a conductive atomic force microscope. So, for those that are unfamiliar with the resistive switching phenomenon, this is basically one phenomenon that happens in one insulating material, electrical insulator, that is placed between 2 metallic materials, 2 electrodes. Here, this is a cross-sectional transmission electron microscope image of the insulating material placed on the metallic electrode. And here there is another metallic electrode that is a conductive tip. So you can see that when we increase the voltage that is applied between the 2 metallic electrodes, the physical properties of the material, the morphology of the insulator changes. And this changes the electrical current flowing between the 2 metallic electrodes. When we apply positive or negative polarities, we can open and close this electrical circuit. So this resistance change is irreversible. because the morphological change is also irreversible. This is the concept idea of one resistive switching device, to make at least two states, the high resistive state and the low resistive state. There are many different electronic devices that can show this property, but actually the fact that makes interesting resistive switching devices is that the change on the resistance is non-volatile. If you just take one transistor also shows resistive switching. When you apply voltage to the gate, the electrical resistance in the channel will change. But once you withdraw the voltage, you lose this high conductivity. So in resistive switching devices, in non-volatile resistive switching devices, this change persists after you switch off the voltage. And this is a very interesting phenomenon. These resistive switching devices have been fabricated with different materials, such as phase change materials, and metal oxides, and magnetic materials, and ferroelectric materials, okay? And depending on the voltage that we apply, we can reach a high resistive state or a low resistive state, okay? We have also seen that this material system can be placed in series with one transistor or with one selector, and this increases the control that I have over the currents across this resistive switching junction. Some recent works, for example, put the ferroelectric material as a gate dielectric in a transistor to achieve a ferroelectric field effect transistor. There are several kinds of structures that are appearing. Every year we can see, every few years we can see a new candidate appears. But the fact that it is a candidate, it doesn't mean that it is going to be something that we could really find a real application in the real world. So here you can see the first application of resistive switching devices, which is as electronic memory. And this is the first application that I will discuss. There are 4. You can find them in our recent review paper in Science. So this application is as memory. If we take a look to the pyramid hierarchy of memories, we see that, and we also take a look to the properties of resistive switching devices made of these materials, phase change, metal oxides, and magnetic, which are the commercial ones. We can see that these properties fit well to fill the gap between dynamic random access memory and NAND flash. Although, depending on the material, we could also achieve properties that approach a little bit more to the embedded DRAM or cache memory. As I mentioned, this is already commercially available. There are some products that are already being commercialized, like memories from Everspin or from Intel and Micron, or, for example, some memories that are inserted in watches from Huawei. In general, these memories have low power consumption, so they are good for the Internet of Things. The global market of resistive switching devices in 2020 was $621 million, which is 0.5% of the total standalone memory market, which is 5.6, which is much bigger. So by 2026, it is expected that this grows to 5.6 billion, which will represent the 2% of the total memory market. This was the first application. There are more. If we have a resistive switching device that shows 2 stable states, you can also use it as a radio frequency switch. But to do this, you need to make sure that the R-on is very small, the resistance in low resistance state, and that in the off state, you have a good capacitance to block the best of the high frequency signal. Another application is to implement a vector matrix multiplication engine. This vector matrix multiplication engine can be done with a crossbar array of membristors, and it is very demanded for the hardware implementation of artificial neural networks. These artificial neural networks, they have several inputs, and they always need to make this kind of vector matrix multiplications to process the information. And if we do this with CMOS transistors, it will be very slow. With the crossbar array of membristors, by Kirchhoff law, I can get this vector matrix multiplication instantaneously. So actually, this is a very big advantage that can save a lot of time and energy for the implementation of artificial neural networks, which is very highly demanded in artificial intelligence product. Here you can see one example in one article in which the authors fabricated one crossbar array of one transistor, one memristor cells, in which the memristor was made of hafnium oxide with tantalum and palladium electrode. And this worked well to do this multiplication. It was an 8x8. Actually, the authors here also fabricate one electronic neuron by using one memristor with silver electrodes that shows volatile resistive switching. So it's the threshold type resistive switching. And with this, they can activate an output when the current across the column surpasses one specific value. So this was another application. And then another additional application is that the memristive devices, the resistive switching devices, show some stochasticity. So that some of the parameters, like the switching voltage or the switching time or the current in one state, show unpredictable fluctuations, because the switching mechanism is not, it cannot be fully predicted with a very high accuracy, because it depends on the atomic structure of the device in each cycle, which is unpredictable. So based on this, one could exploit this source of randomness in an electronic circuit to produce random numbers, 1 or 0s. So this is an output that fluctuates at high frequency between 1s and 0s in a completely random way. And this is good because with this, we can generate true random numbers, which is the typical application that we use when we make, for example, online payments with our phone. We receive a one-time password that has to be completely random so that nobody can hack your bank account or your money transfer. So this needs to be done with hardware, because with software, it could be susceptible to be hacked. And we already published one paper last year in which we constructed one system in which the randomness source is 1 boron nitride. And this circuit, the aim was to produce random numbers. But also, if we have a large population of resistive switching devices, and we apply one stress so that 50% of these devices will switch, then we will not know which devices are going to switch, because again, this depends on the atomic structure of the devices. So we will have random changes, and these changes can be used as a fingerprint, as a physical and clonable function for this device. Let me just mention, before going deeper into this topic, that the resistive switching topic is of very high interest right now for the community. Here I just show you one example for the papers published in 2018 by Nature Electronics, which is the top 1 journal in the JCR category of electrical and electronic engineering. These are the top 10 most cited papers in the journal, and among them, 7 of them are related to resistive switching devices, which means that this is a really good, from an academic point of view, this is also a very good topic to be working on. Okay, so now I'm going to talk about the importance of this miniaturization. Here I show you one top view SEM picture and one cross-sectional TEM picture of one resistive switching device. As you can see, this resistive switching device can be fabricated very, very small. This is only 30 nanometer. And here we could even put these wires much closer to each other to make this distance, this gap smaller, and then we could put more devices next to each other. This is a big advantage of memristors. They have a very high integration density if we make them very small. In fact, they can also be fabricated in a three-dimensional structure, and this can be done by putting the bottom electrode in this way, separated by, one on the other. Here are the platinum bottom electrodes, and then we put the insulator along the edge of one cavity that has been patterned in the wafer, and then this part here will be the top electrode. So we have one memristor laterally in this way, another memristor laterally in this way, so you can see a better picture here. So this is also very interesting. Actually, in some studies, we can also find that the memristor can be integrated in CMOS microchips on the CMOS transistor. Here you see the transistor. This is the metallic via in the microchip, and here you see the memristor that is integrated on top of the via. It's also very small. So let's see what is the main challenge of these resistive switching memories. If you go to the shop to buy resistive switching memories, here we go to the shop of Fujitsu, to the website, and we check what are the properties that the manufacturer gives in the data sheet. So if you go here, you go to product line, and then you click on the data sheet, and then you go to what is the right endurance, you see that is 500,000 cycles. Okay, this resistive switching memory is made of metal oxides. We also have other companies that make resistive switching memories. For example, the company Intel and the company Micron partner to make phase change memories, and they offer memories, and in their data sheet they say that the endurance is 10 million cycles. Okay, 10 million cycles. That's the specifications of the commercial product. However, if we check academic papers, we will see that in this material, for example, taking the example of metal oxides, people report endurances that are much higher. You see, much higher. And actually, many of these studies, to start with, present one claim of high endurance based on one plot that contains very few data points. You see, here they are claiming 10 to the 12 cycles, showing a plot that has only 50 points. Okay, so this is something that we should try to avoid. Still, there are some works that use plots with a lot of points in which you cannot distinguish how many points you have, and they make very high endurance claim. So what is the trick here? Because there is for sure a trick, because the papers say high endurance more than 10 to the 10 cycles, but the memory never promise you more than 10 million. So there is a big gap here of few orders of magnitude. So what is the problem? The problem is this. The problem is the device area. These works measure the endurance in big resistive switching devices. They are all big, very big. While the memories that you buy, resistive switching memories that are integrated in commercial products, the device size is very small because you want a very high integration density, especially for memory and for artificial neural networks. For radio frequency switches and for data encryption, for true random number generators or physical and kernel functions, the size can be relaxed. That is not a high integration density product. However, for high integration density applications like memory or artificial neural networks, you need a high integration density. So this is the main problem. This finding may not necessarily apply to small devices. Actually, here I show you again one comment regarding the method that many of the papers use here to show plots that contain very few data points. You can see better what I mean here. This is the comparison. We never consider plots like this, which are placed in many articles. We always think this is much better, because it shows more reliably the resistance in each cycle for many devices. So if we take into account only papers that use this method, and that use a very small device area, now we find very few articles promise you more than 1 million cycles, you see. And here we have one that is strikingly high, but this is a threshold type resistive switching. It's a little bit different. For bipolar, you see, it's very, very few papers promise you more than 1 million cycles, okay? Here is the big difference. So let me show you what is the difference, okay? So you can see it a little bit more clear. So many studies, as I mentioned, have measured large memristors, and they think the performance is very promising for information storage of neuromorphic computing, but again, the size was too big. They didn't demonstrate at the nanoscale. So let me see. This is what let me show you what most people does. Is something like this. They put an insulator on a sample that has a bottom electrode, and using a mechanical shadow mask, they pattern some electrodes. Some people use the laser pattern shadow mask. Actually, I used this when I started my group. And after you put the electrodes, this is what you get, okay? So with the mechanical shadow mask, this is a total disaster. With the laser pattern shadow mask, it's a little bit better. Then they have to apply electrical stress. So many people, what they do is they just scratch with the probe station tip on the surface of the insulator, which is not good. What we should do is a lithography and then do like this. However, I have to say that I have seen talks from many scientists who work in universities that don't have enough resources to purchase one mask aligner, and then they use the method of the shadow mask, okay, which is totally reasonable and decent, but the readers of the papers have to keep in mind that if you don't measure a small device, you cannot claim that this memristor is promising for information storage or neuromorphic computing, no matter what you see, because it's big size. So let me show you why the size is so important. First of all, there are a lot of papers that say that when you make the device smaller, the dielectric breakdown voltage increases a lot. And this can be seen, for example, in metal oxides. You have a metal oxide, and you make a large device, you put it between two electrodes. This metal oxide will have some native defects. When you apply voltage, you will generate a conductive filament at the weakest point of the sample, which will be in this point, okay? And this filament will have some properties. Now imagine you measure this device and you observe an endurance of 10 to the 12 cycles, okay? This is an excellent memristor. The filament has been formed in a weak place under a low energy, so it is reversible. It can be destroyed. Now, let's take the same identical material, but we put small electrodes. Now, when we put these small electrodes, what happens? At this point, I will need high voltage to break the material because there is no defect. So I will induce a filament. And in this point where I have a defect, I will need a smaller voltage. And in this point where there are three defects, I will need an even smaller voltage, okay? This voltage is the same than the one of the big device, okay? Because the filament forms here. Okay, but we should be aware of something. When I increase the voltage, the energy I'm giving is different. And therefore, when I give more energy, the filament will be wider and the composition will be also different because I may be producing the migration of metallic atoms from the electrodes, for example. So you see in this filament, there is no metal electrode, metal penetration from the electrodes in the filament, and it may live very long. But in this one, which is much wider, or in this one, we also have metallic atoms from the electrodes. So basically, if you do this, maybe this one switch a lot of times, but most of the others will not switch or will switch few times because such a wide filament produced at high voltage will not switch so well. So you have seen that, the measuring a big device and measuring small devices is completely different, especially in the terms of statistics. And actually, what we want in resistive switching devices for memory and for computation is that all the devices behave identically, okay? This is the ideal behavior. This will be something acceptable in which we can detect the two states, even if there is cycle-to-cycle variability and device-to-device variability. However, this is what happens most of the time, that we cannot distinguish all the cycles for all the devices. Actually, here I show you two schematics. One example is for devices that contain some local defects, let's say grain boundaries. When you make the device big, when you make the device small, okay? So for the big device, the difference between one device and another in terms of defects area will be small. You see, this is, if we consider this to be the 100% defect area, this will have minus 11%, this will have plus 11%. If we make the devices smaller, we will have devices that have absolutely no defect, some that will have one defect, some that have two defects. So this is a difference of minus plus 100% and plus 100% respect to the reference one. So this is going to behave completely different to this one, while this one and this one and this one will behave similarly. The same happened. This was for one material that has grain boundary. This is for a liquid phase exfoliated two-dimensional material. Here you see for the smaller devices, this has no defects and this has a lot of defects. So the change on the defect area is huge. So this is a big problem that affects the yield and the variability and the performance of the membristors. But in fact, this is applicable to other devices. Here you can see the variability of nano-sized 2D materials-based transistors, and you can see that some studies report one single value, which is normally the record, for the on-off current for these transistors. However, in this other paper from IMEC, the authors fabricate small transistors with different channel length. And what they observe is that you can see as they reduce the channel length, the device-to-device variability increases a lot. Okay, so you make the devices smaller, the variability from one device to another increases like crazy. Okay. Okay, so now in the last part of the talk, I would like to talk about the resistive switching observed with the conductive FM. In fact, there are different phenomena here. This is the first that I would like to show you. We take two samples, sorry, that are made of hafnium dioxide. One of them is amorphous, has been heated below the crystallization temperature, and one is crystalline that has been annealed at above the crystallization temperature, which is 900 degrees. We can observe big differences on the leakage current. This one is much more homogeneous than this one. Okay, this is a sequence in doing zoom outs. And we can see that here, this is much more homogeneous than here. However, when there are weak spots here, these drive much larger current than these ones, okay? You can see here. These spots drive more current than this one, although the background current is larger in the amorphous one, okay? When we apply sequences, we observe one phenomenon in the amorphous sample, which is that there is reduction of the current with the number of scans. This is a phenomenon called charge trapping. And this phenomenon doesn't take place in most of the areas of this sample. However, I have to say that in the highly conductive spots, the charge trapping effect is huge, okay? You see this reduction is very, very big. This reduction is very, very big, but this reduction is only a factor of 2, okay? Which is the background signal here. We have also analyzed samples that are very, very polycrystalline with a conductive atomic force microscope, and we can see that the grain boundaries show much higher current than the grains in the hafnium oxide. So actually, if now we try to make membristors with this sample, the membristor that is inside the grain and the membristor that is at one grain boundary, they will show very different properties. And actually, this is what we did in the next experiment. Here, this is an experiment that I did when I was postdoc at Peking University. So my friends in Peking University, they observe resistive switching in 13 nanometer thick hafnium oxide that has been annealed at 600 degrees. This means it's polycrystalline. They make big electrodes of 50 micrometer by 50 micrometer, and they measure these. There is a dielectric breakdown, but this can be recovered. And after that, they see switching between two states very reliably. But they have no idea what is producing this behavior. So what I did with the conductive AFM is to try to measure many single locations with the tip randomly. And what we observe is that at most the locations, there is no resistive switching, while few locations that show a breakdown voltage that is similar to the one observed in the devices, these ones can show resistive switching reliably, okay? In the next step, we scan the surface of the samples, and we observe that this resistive switching only takes place when the tip of the AFM is placed at a grain boundary. If we place the tip at the grain, there is no resistive switching phenomenon. This later, by making some Kelvin-proof force microscope measurements, we also observed that this is related to a higher density of defects at the grain boundaries. And actually, by making current maps with different voltages, we could observe statistically the presence of filaments with different diameter and different current. I have to emphasize that this is a non-standard experiment that cannot be done with most conductive atomic force microscopes, because one conductive atomic force microscope only can apply voltages from plus 10 volts to minus 10 volts and can measure currents that expand a few orders of magnitude, maximum 3. So this resistive switching cannot be observed, and in many devices, you need to apply a very large voltage to induce the dielectric breakdown when the material is fresh. And sometimes this is up to 20, so it cannot be applied. Moreover, if you measure in air, you cannot measure two polarities for one material that contains oxygen, like hafnium oxide, because you will have something called local anodic oxidation due to water splitting at the tip sample junction, because there is water from the environment. So what we did is, first, we measure in vacuum to avoid the problem of the polarity. And second, we connect the semiconductor parameter analyzer to the tip of the AFM to be able to apply high voltages and measure high currents. Okay, so this is something that we did very few years ago, and it was really well. Actually, this was copied by other people later. Something that we can also do, because some people criticize this experiment because they say the filament that we measure has been induced with the tip of the AFM. So it's not the real filament we will see in one device, okay? This experiment is good to understand which locations produce the filament, but not the properties of real filaments. So what we do is we measure a real device, then we etch the top electrode, and then we scan with the tip of the AFM. And then these filaments that are here are produced in a real device. And then we can analyze them with the tip of the conductive AFM. We observe a very interesting thing, which is that in the high resistive state, all the filaments have similar properties, but in the low resistive state, we see one filament that is dominant among all the others, which means that there will not be an area dependence in the low resistive state, which is actually what has been observed also at the device level by measuring devices with different sizes. Actually, this method of etching the top electrode can also be applied to other devices, such as transistors. And in this article, we find what is the difference on the distribution of the stress when applying a negative bias temperature instability or channel hot carriers stresses to the field effect transistors. If you are interested, you can check more details here. And another thing important is that when you etch this material for the top electrode, you may be damaging the underlying resistive switching material. I mean, there is no experiment that doesn't change the boundary conditions. Everything makes some little change. So we need to make many different experiments to understand better the resistive switching. And here we propose one structure that is very interesting, in which we stress the dielectric material using a liquid. And the liquid is very interesting because then we can rinse it out, and then we can scan the surface of the sample with SEM, with conductive AFM, etc. So the fabrication of this structure is relatively simple. Okay, it just very 5 or 6 easy steps. After that, when we apply the voltage to the ionic liquid, we can observe the resistive switching. Here, initially the resistivity is high, then we switch it low, then it's back high. Okay, we analyze devices with different areas. We observe there is area dependent, so there is no dominant filament. And then after that, in the fresh sample, after the first set, after the first reset, and after the second set, we can make current maps, and we can understand which is the size of the filament and the currents driven by the filament statistically in this material, which is something really nice. Actually, we combine this with OJ electrons, with nanosims, and we could find out that these filaments are made of oxygen vacancies because the oxygen has moved towards the surface of the material as we apply the electrical stress. Another thing that we have done recently with conductive AFM is to measure synaptic plasticity. Synaptic plasticity is something that takes place in resistive switching devices, and that is in some resistive switching devices, and that it can be very useful for some kind of artificial neural networks. With a standard AFM, we observe that the device shows threshold type resistive switching. Okay, because this resistive change that we observe between the forward and the backward is not volatile. It's volatile, sorry, because in the next IV curve, I recover the initial. So in order to see what happened during the recovery time, we will need to apply fast pulses. However, this cannot be done with a standard conductive AFM. So what we did is to connect the semiconductor parameter analyzer, then we can see the relaxation process. So the synaptic plasticity takes place when the pulses are so near one to each other that there is no time to relax, and then the conductance of the material starts to increase. This is what we call synaptic plasticity, and it can be measured with the conductive AFM. We demonstrated this recently, and actually already another paper from China came where they already replicate this. So if you are interested, you can check the small paper from Fei last year. Finally, this is something we are very interested right now. We are trying to replicate what this paper did before, which is the measurement of the temperature of a conductive nanofilament across the device, the memristor device. and one can see, evaluate what is the temperature of the filament, which this is interesting, especially in devices that are made of two-dimensional materials, because two-dimensional materials have a very high in-plane thermal conductivity. Actually, in my group, we have also done this. Faye did this during her postdoc, and we already published one article about this. So, in conclusion, the properties of large devices may differ a lot from those of small devices. Device-to-device variability is a major concern in ultra-scale technologies. The conductive atomic force microscope is an ideal technique to analyze multiple nanoelectronic phenomena, and the setup of the conductive FM can be modified to observe novel electronic phenomena. If you are interested on gaining more information, you can check our recent publications. And also, just to mention that I have recently moved to the King Abdullah University of Science and Technology, and we have very generous scholarships in case anybody wants to do PhD or postdoc in my group. And that's everything. Thank you very much.
Thank you. Thank you very much, Professor Lanza. Yeah, Professor Lanza shared with us very detailed information about how to use the c-afm to test the resistive switching and other electrical behaviors. So now in the chat, we have got a couple of questions. So let's first look at the first one. The first question is, the stability and the variability is pretty important for electronic devices. How to improve them during the miniaturization or at the nanoscale? Thank you.
Well, the answer I will say is, first of all, measure at the nanoscale many devices. Then you will understand how good this stability and variability is. First, measure many devices. And then tune your recipe for, if you are fabricating, for example, memristors, you may need to adjust this. If you are fabricating transistors, maybe you need to tune the number of defects in the channel, and you may tune the electrical resistance. There are papers that say that depending on the material of the electrode, depending on the geometry of the electrode, you can reduce it. For memristors, normally what we adjust is the diffusivity of the metal into the resistive switching material, the thickness of the resistive switching material, things like this. So there is no magic recipe. You have to check the material you are working with, which are the electrodes, and then make decisions on how to adjust that. But normally, thickness of the material, device size, and diffusivity of the metal into the resistive switching device are the main factors to take into account.
Yeah, okay, thank you. So let's look at the next question. How about the repeatability of c-afm test when measuring the resistive switching?
Yeah, this is a very good question. The tips degrade fast. The tips get attached some dirt, and the tips and the system has a lateral drift. You cannot measure in one point many IV curves. It will take too long, and the tip slowly move. And also, if you measure a little bit high currents, the current density is huge. So this is a problem. Okay, I have shown you several slides in which I show the RAM voltage stresses. Okay, when I started, to be honest, I am more now a fan of the maps, because for the maps you can apply lower voltage and you will find which are the weak locations. So I am more a fan of the maps, because you don't need to go to such a high currents in order to induce the resistive switching, because there will be, I mean, with the maps you can catch the weakest locations. With the tip is more with the IV curves it's more difficult to catch the weakest locations, but with the map it's better. So I will say If you want to see better reproducibility, use maps. Don't put the tip in one specific place. Using maps probably is going to be better.
Okay, thank you, Professor Lanza.